In today's video, we are going to explore the most fascinating part of circle chapter from class 11 of coordinate geometry, which is radical axis and radical center. Watch the video till end because here we are going to explore not only the definition of these two parts, but also the important properties associated with radical axis and radical center. Learning these two conceptions are very important for solving complex circle problems, projective geometry, or geometric transformation. So let's dive into our today's video. First of all, we must know what is radical axis. Radical axis is the locus of a point moving in a plane in such a way that the tangents drawn from this point on the given two circles, the length of the tangent, they are always equal. Let us say we have been given two circles like this, and there is a point somewhere here. Now we have to find out the locus of this point. Let us say this point be P and any point on the locus be H, K. Now we have been given two circles. Let us say the two circles be, the first circle is x square plus y square plus 2g1x, 2f1y plus c1 equals to 0. We are using the general equation of the circles. 2f2y plus c2 equals to 0. Let us say this is my s1 equals to 0 and this is my s2 equals to 0. Now, if I draw tangents from this point on these two circles, then according to the definition, the length of these two tangents, PA and PB, they must be equal. Now we all know that the power of the point P with respect to the circle S1 equals to 0 is h square plus k square plus 2g1h, 2f1k plus c1 is 0. This is the power of the point P with respect to the circle S1 equals to 0. And same thing, the power of the point P with respect to the circle S2 equals to 0 is okay. Now we all know that the length of the tangent is square root of the power of the point. This is the length of the tangent for the circle S1 equals to 0 drawn from the point P. And the length of the tangent drawn from point B on the circle S2 equals to 0 is given by, so let me square both sides. And now we can easily see that h square k square will go off. So we are left with 2 times g1 minus g2h plus 2 times f1 minus f2k plus c1 minus c2 equals to 0. Therefore, the equation of the locus of the point P is Am I correct? Okay, so this is the locus of the point P, and we can see that it is nothing but a straight line. And this line is what called your radical axis. Now, if you have a keen look on the equation of the radical axis, then we can easily see that you can get this equation of the radical axis very easily simply by subtracting S1 minus S2 equals to 0. If I subtract the given two equations, we are going to have the equation of the radical axis. So very important point to be noted. And we have to remember that whenever we have been asked to find out the equation of the radical axis when two circles are given to us, we will simply subtract the equation of one circle from the other to get the equation of the radical axis. Is it clear to all? Have you understood this? Okay. Now at this point, we are coming to a very important conclusion, which is irrespective of the position of the circles, there is always a radical axis. What I told you, irrespective of the position of the circles, there is always a radical axis. Like, if I say that there are two circles which are neither intersecting nor they are touching each other, in that case, your radical axis will be this one. Okay? So this is the radical axis when two circles are neither intersecting nor touching each other. Now suppose there are two circles which are touching each other. Okay? They're touching each other. In that case, the radical axis will be this line. Right? And if you observe, you will find that this line is basically the tangent to these two circles. Radical axis, in this case, when the two circles are simply touching each other externally, then your radical axis and the common tangent, in this case, this common tangent is what called your transverse common tangent. So whenever the two circles are touching each other externally, the radical axis and the transverse common tangent, they are the same line. Okay? Now, if the two circles are intersecting each other, if two circles are intersecting each other, let us say this is one circle, this is another circle, they are touching, intersecting each other, then the radical axis will be this one, the line which is passing through the 2 points of intersection of these two circles. In this case, your radical axis and the common chord, they are the same. This is what? What is this? AB is basically your common chord for both the circles. And this common chord will be same as your radical axis. So in this case, your radical axis and common chord are the same line. Is this clear? When two circles are intersecting each other at two distinct points. Now, if the circle is touching each other internally, suppose these are the two circles, they are touching each other internally. In that case, this will be your radical axis. At the same time, you observe this line is basically the tangent to these two circles, and this common tangent is what called your direct common tangent. So when two circles are touching each other internally, the transverse common tangent is same as your radical axis. I'm sorry, the direct common tangent is equals to its radical axis. So radical axis and direct common tangent, they are the same line. Is it clear? Now suppose if there are two circles, one inside the other. Let us say this is one circle and this is another circle. Now the question is, in this case also, can we have a radical axis? Answer is yes, we can have. The radical axis will be something like this. The radical axis will be something like this. Okay? So we have seen in all those 5 cases, irrespective of the position of the circles, we can draw radical axis. But when two circles intersect each other, in that case your radical axis becomes its common chord. When the two circles are touching each other externally, the transverse common tangent and the radical axis, they are the same. And when two circles are touching each other internally, the direct common tangent and the radical axis, they are the same. But there is one case where your radical axis is not defined. Be very careful. Irrespective of the position of the circles, you can draw a radical axis, but except this condition. What is that? If two circles are concentric, in that case, the radical axis is not defined. If suppose this is one circle and this is another circle which is concentric to this circle, in this case, radical axis is not defined. Is it clear to all? Have you understood this? I have taken all the possibilities of the position of the circles, and we have seen that yes, in everywhere radical axis is possible, irrespective of the position of the circles. But there is only one condition, only one way in which radical axis is not defined: when the two circles are concentric. Is it clear to everyone? Okay, now let's come to the properties for radical axis. Properties of radical axis. Now, property, you always remember, whenever we are discussing property, it means it is true for all the cases that we have already discussed. For illustration, I am going to take a particular case, but again I am mentioning it is true for all kinds of circle, right? Whatever we have discussed so far. Let us say we are having two circles which are neither intersecting nor they are touching each other. And let us say the equation for this circle be S1 equals to 0 and this is S2 equals to 0, where S1 is x square plus y square plus 2g1x plus 2f1y plus c1 is 0, and S2 is x square plus y square plus 2g2x plus 2f2y plus c2 equals to 0. Okay? Now the first property that we are going to discuss about is that whenever we join the two centers of these given two circles, the line joining the two centers of these two given circles, let us say A and B, it is always perpendicular on the radical axis. Again, I am telling you, I have taken this particular case, but it is true for all kinds of circles we have discussed so far. So, the radical axis will be always perpendicular on the line joining the two centers of these two circles. Now, let me prove it. What is the equation of the radical axis? The equation of the radical axis we have already discussed. It is S1 minus S2 is 0, implies 2 times plus C1 minus C2 equals to 0, right? So, what is the slope of the radical axis? The slope will be minus G1 minus G2 over F1 minus F2, correct? This is the slope of the radical axis. Now, the center of the first circle is minus G1 minus F1 and the center for the second circle is minus G2 minus F2. Now, what is the slope of AB? Slope of AB is F1 minus F2 divided by G1 minus G2, correct? So, this is the slope of the line AB and this is the slope of the radical axis. Now, we can clearly see that if I multiply these two slopes, we are going to have, if we multiply these two slopes, we are going to have minus 1, which clearly says that the radical axis and the line joining AB, they are perpendicular to each other. Is it clear to all? Okay, let us come to the next property, number 2. If you draw tangents to these circles, whether it is direct common tangent or transverse common tangent, whatever tangent you draw, which is a common tangent. Let me just draw this one. Let us say this is my direct common tangent and let us say this is my transverse common tangent, right? This is the transverse common tangent. Okay. Now, the property states that the radical axis, just 1 second. Okay. So now, this direct common tangent, let me just give a name, CD. CD is the direct common tangent and let us say it is intersecting the radical axis, let us say at M. Now this property states radical axes always bisect its common tangent. Is it true or not? Please check this one. This direct common tangent is intersecting the radical axis at the point M. And from the definition of radical axis, we know that from any point on the radical axis, if you draw tangents to the two given circles, their lengths are equal. It means that your CM, because CM is the tangent drawn from M on the first circle, and MD is the tangent drawn from the point M to the second circle. Therefore, your CM and MD, they are equal. It means what? M is the midpoint of CD. That is, radical axes always bisect the common tangent. In this case, we have proof for the direct common tangent. The same rule is applied for the transverse common tangent also. This transverse common tangent is intersecting the radical axis, let us say at N. So from N, this N, say this is T and let us say this is P. So your Tn and Np, these are the two tangents drawn from the point N. This way we can think of. And we know from the radical axis definition that Tn must be equals to Pn. So the second property states that the radical axis is always going to bisect its common tangents. Whether it is direct common tangent or transverse common tangent doesn't matter. It is always going to bisect those tangents. So this is property number 2. Now let us come for property number 3. Let us consider, let me just go for the next page. And let me draw two circles first. So this is my one circle and this is another circle. Okay. Now there is the equation of this circle is again, I'm not writing it anymore. It is already written there. So I can do one thing. I can copy this one. I can take it to that page. So these are the equation of the two circles. Now, look it very carefully. This third property is a wonderful property. The third property states that if there is a circle which is intersecting the given two circles orthogonally, then the radical axis of this given two circles will pass through the center of this third circle. It means that if there is a circle which is intersecting the given two circles, let us say orthogonally, let me say the equation of this circle be S3 equals to 0, then the property states that the radical axis of S1 equals to 0 and S2 equals to 0 is going to pass through the center of this circle, right? So how to prove this? But before that, we must know what is orthogonal intersection. Two circles intersect each other orthogonally means what? The angle between the two circles is 90 degrees. Now, how we measure that? At the point of intersection, we draw tangents to the respective circles, and then we find the angle between these two tangents, which is same as the angle between these two circles. In this case, that angle is 90 degrees. That's exactly what orthogonality means. Okay? So, if I draw a tangent at S1 at this point, the tangent will look something like this, okay? And if I draw a tangent to S3 at this point, it is going to look something like this, okay? Now, by the problem, this angle is 90 degree. Because these two circles intersect each other orthogonally. So this angle is 90 degree. It means that this line, that is the tangent to S3, will become normal to S1. That is, this line is definitely going to pass through the center of S1. Similarly, the tangent at S1 will become the normal to S3. Hence, it is definitely passing through the center of S3. Okay? Similarly, at this point, if I draw tangents to circle S2 as well as circle S3, this angle is again going to be 90 degree. So, this tangent to S2 will now become the normal to S3. And hence it is passing through the center of this circle S3, as well as the tangent to S3 is again the normal to the circle S2. Hence it is passing to the center of S2. Is it clear? Therefore, you observe carefully, therefore, these are the two tangents. Let me give a name. Let me say the center of this be A and this point of intersection be B and this point of intersection be C. So now we can see that your AB and AC, these two lengths, they are same. Why? Because they are the radius of the same circle. As these two lengths are same, these two are basically the tangent to the two circles S1 and S2. And the length of the tangents are equal. So what do you mean by that? It means that point A is somewhere on the radical axis of the circles S1 equals to 0 and S2 equals to 0. It's obvious. Because according to the definition of radical axis, from any point on the radical axis, if you draw tangents, the length will be equal. And in this case, your AB and AC, which are the radius of the same circle, hence they are equal. Therefore, the length of these two tangents to two circles S1 equals to 0 and S2 equals to 0, they are equal. Hence, we will say A is a point on the radical axis of S1 equals to 0 and S2 equals to 0. Therefore, this property has been proved that whenever there is a circle which is intersecting the two given circles orthogonally, then the radical axis of the first two circles is going to pass through the center of this third circle. Is it clear? Okay. Now, you can do this problem by using coordinate geometry also. Okay? Because S1 is given to us, S2 is given to us. Now, we will assume that, let us say, S3, that is this circle, be x square plus y square plus 2 gx plus 2 fy plus c equals to 0. We can say in that way. Now, as S1 and S3, they are orthogonal. So, we know the condition of orthogonality. It is basically, okay, let me just do it. It will be 2g1g plus 2f1f, which is equals to C1 minus C. Similarly, S3 and S2, they are also orthogonal to each other. So we will say 2G2G plus 2F2F equals to C2 minus C. Okay. So let me just subtract this 2. We are going to have F1 minus F2F C1 minus C2. Okay. Now, what is the equation of the radical axis? S1 minus S2 is 0. That gives us 2 times G1 minus G2X, 2 times F1 minus F2Y plus C1 minus C2 equals to 0. Okay. Now, what is the center for this circle S3 equals to 0? it is minus G minus F. Now, if I put this center in this equation, we are getting so we are actually having 2G1 minus G2G 2F1 minus F2F equals to C1 minus C2, which is actually true. It means that the radical axis is passing through the center of the third circle. Is it clear? So first I have proved by using geometry properties, and then I have proved the same by using our coordinate geometry, right? Okay, so let's move for the next property. It states that if there are three circles, and if we take the three circles pairwise, these are the three circles. Now, if we take these three circles pairwise, then this property states that their radical axis, we are going to have three radical axes in this case. The property states that these three radicals will be concurrent. That is, all these three radical axes are passing through the same point. That we have to prove. Okay, let us say this equation be S1 equals to 0, this equation is S2 equals to 0, and this is S3 equals to 0. Now, what is the equation of this radical axis? It is our, let us say this is L1, which is nothing but S1 minus S2 equals to 0. At the same time, what is the equation of this radical axis? It will be S2 minus S3 equals to 0, right? Now we have to prove that these two radical axes, they are actually meeting at the point, let us say P. Now we have to prove that the third radical axis is also passing through that point. Now from the family of lines, we know that any line which is passing through the point of intersection of two given lines is written as lambda times equals to 0. Now here lambda is a parameter. Lambda can take any value. Let us say lambda is 1. Then what happens? S1 minus S2 plus S2 minus S3, this gives us 0. So that implies S1 minus S3 equals to 0. And S1 minus S3 is nothing but the radical axis of S1 and S3. So what we have proved? We have proved that the third radical axis is also passing through the point of intersection of L1 and L2, which are the radical axis of the first two and the second and third circles radical axis. That is, all the three radical axes are concurrent. Okay? And this point is a special point where all the three radical axes are meeting. It is a special point. And this point is what called your radical center. Is it clear? So, till now, we have completed the complete radical axis. Now we have entered into radical center. I have already described what is radical center, where the radical axes are meeting. Circles, three circles are there, and we have taken circles in pairs. Their radical axes, all the radical axes are concurrent, and this point is what called your, the concurrent point is what called your radical center. Is it clear? So now let's move for some properties of radical center. Properties of radical center. Okay? The first property states that if there is a circle which is intersecting three given circles orthogonally, then the center of the fourth circle will be the radical center for these three given circles, and its radius will be the length of the tangent drawn from the radical center to any of these three circles. That is, if there are three circles, let me just draw the circles first. There are three given circles. And what they are saying is, if we can draw a circle, the fourth circle, in such a way that it intersects these three given circles orthogonally, then we have to prove that the center for this circle of the fourth circle is nothing but the radical center for the three given circles S1 equals to 0, S2 equals to 0 and S3 equals to 0. Okay? The moment we prove this, then we will prove that the radius of this fourth circle will be the length of the tangent drawn from this point to any of these circles. Now, how to prove this one? See one thing. We have learned one property. Just for a time being, just forget about S3 equals to 0. Only think about S1 equals to 0 and S2 equals to 0. Now, this circle is intersecting these two circles orthogonally. It means that the radical axis for S1 equals to 0 and S2 equals to 0 will pass through the center of this yellow circle. Yes or no? Let me just denote this yellow circle by S4. Okay? Let us say this is my S4 equals to 0. So the radical axis will definitely pass through the center of this S4. Okay? Let me draw that. Let me draw the radical axis. So this is my radical axis which is passing through the center of the circle S4 equals to 0. Right? Now, consider S2 equals to 0 and S3 equals to 0. Again, S4 equals to 0, this circle is intersecting S2 and S3 orthogonally. It means the radical axis for S2 equals to 0 and S3 equals to 0 will definitely pass through the center of this fourth circle, which is S4 equals to 0. That is, the radical axis for S2 and S3 is this, which is passing through the center of S4 equals to 0. Similarly, for S1 equals to 0 and S3 equals to 0, for these two circles, this yellow circle, that is S4 equals to 0, is intersecting these two circles orthogonally. It means the radical axis for these two circles will definitely pass through the center of the circle S4. So, this is the radical axis and which is passing to the center of the circle S4. Now, observe that these three radical axes are passing through the center of the circle S4. And we all know that radical axis of three circles taken in pairs always meet at a point which is called your radical center. So we have proved that the radical center for these three circles is same as the center of this fourth circle. This fourth circle is intersecting the three given circles S1, S2 and S3 orthogonally. Is it clear? Now, if I draw, let me say, if I draw a tangent from this point to any of these circles, let us say this one, or let us say this one, or let us say this one. Okay, these are all the tangents drawn from the radical center to these three given circles. Okay, it is not exactly coming, but it's okay. We will understand that. Let me not draw this one. We will understand that from this point, because this figure is not the accurate one, we are actually drawing a rough figure. Now, from the radical center, we all know that if we draw tangents to any of these circles, let us say this one, or this one, or this one, or this one will be actually the, let us just assume that it is like this, okay, and this is like this. It seems like it is cutting, it is actually not cutting, it is a tangent. Now, from the radical center, if you draw tangents to two circles, their lengths will be equal. That is the definition of radical axis. Therefore, all these lengths, they are equal. Okay? Which is actually the radius of the fourth circle. So how we got the radius of the fourth circle? It is nothing but the length of the tangent drawn from the radical center to any of these three circles. Eventually they are all equal. So that will be the radius of the fourth circle. So that is property number 1 for the radical center. Now let's move for another very interesting property for radical center. It states that if you draw three circles on three, let me first draw the diagram and then I will explain what actually this property demands. Okay. Now see, the property states that if there is a triangle ABC and you draw a circle on each of these three sides of the triangle in such a way, taking the length of the triangle, length of the sides as its diameter, then this property demands that the radical center that you are going to have for these three circles will be same as the orthocenter of the triangle ABC. This is the property. So now you see the triangle is ABC and I have drawn three circles, each on three sides of the triangle taking as a diameter of that circle. Now we have to prove that the orthocenter of the triangle ABC is same as the radical center for these three circles. Well, let me do one thing. From the point A, let me just join this point. Okay? Let me just join this point. Okay? I am considering these three circles. Let me just write ace of AB. Ace of AB means the circle drawn on the side AB. This is my ace of AC and this is ace of BC. Now, once I join A, let us say this point be M. Now, look it very carefully. It's a very important point. What is our goal? Our goal is to prove that the radical center for these three circles is same as the orthocenter for the triangle ABC. Orthocenter means where the three altitudes meet. Now, If I join this point, BM and MC, look it carefully. Since this point M is on the circle SAB, so this angle will be 90 degree, because we all know that angle in a semicircle is always a right angle. And now similarly for the circle SAC, this angle is again 90 degree, because this is also the angle in a semicircle. Therefore, this angle is 180 degree, right? Therefore, we can say that this point, the point M, point B, M and C, they are all lying on a straight line. Is it clear? B, M, C, these 3 points are collinear. Therefore, this M point is basically on this, on the side BC. Okay, since as I told you, my diagram is a rough diagram, that is why we cannot get the exact figure. But now we can understand by mathematical proof that this M point is nowhere other than on BC. And so this point is basically M. Let me just remove this. So this is 90 degree, okay? This is 90 degree. Therefore, AM is perpendicular on BC. Is it clear? So the first thing that we have proved that AM is what? It is basically the radical axis. What is AM? It is the radical axis for the circle SAB and for the circle SAC. Okay? And we have seen that this radical axis is perpendicular on BC. Now, let us consider the circle SAB and SBC. SAB and SBC. Look at carefully. For these two circles, if I join this point with B, now see this one. For the circle SAB, as AB is the diameter, so this angle will be what? 90 degree. Again, the same logic, angle in a semicircle is a right angle. Similarly, for the circle SBC, this angle will be 90 degree, as BTC is, T is a point on the semicircle of the circle SBC. And angle in a semicircle is always a right angle. Therefore, your BT, which is basically the radical axis of SAB and SBC, is perpendicular. That is, BT is perpendicular on AC. Just now we have given you the argument why it is perpendicular and why this point T is lying on AC. So we have seen that your BT is perpendicular on AC, as well as AM is perpendicular to BC. Okay. Now in the similar way, if you take SAC and SBC, you will find that this radical axis, okay, let me give a name, let us say CP. So CP, the radical axis, is also CP, which is actually the radical axis for the circle SAC and SBC. Your CP is again perpendicular to AB. Is it clear? Therefore, we can see that these three radical axes are meeting at this point. Yes or no? So this is basically this point. Let us just give a name, this point as Q. So your point Q is basically the radical center for these three circles, as well as this point Q is a point where all the three altitudes of the triangle ABC are meeting. Therefore, your point Q is also the orthocenter for the triangle ABC. So what we have proved? We have proved that the radical center for these three circles, which are drawn on the sides of the triangle ABC, taking the length of the side as the diameter, the radical center and the orthocenter for the triangle ABC, they are the same point. Is it clear? So this is our second property for radical center. Okay? So these two properties are important. So for the JEE aspirants, these two properties will help you a lot in solving problems. So radical axis and radical center, we have discussed the important aspect of these two things, these two parts and these two subtopics of circle. At the same time, we have proved all the properties. So that's all for this video. See you very soon in my next class. Till then, take a very good care of yourself.